Distributed systems rely on multiple physical machines acting as a single, unified entity. The fatal flaw in this design is network reliability. A connection between nodes can suddenly sever in a millisecond, fracturing the cluster. If developers attempt to coordinate these machines using traditional blocking mechanisms, like distributed locks, a network failure becomes catastrophic. If the node holding a lock drops offline, that lock remains held. Healthy nodes are left stuck, waiting indefinitely. Worse, a fractured network can create a split-brain scenario. The isolated nodes assume the original leader is dead and elect a new one, while the old leader continues operating on the other side of the partition. Two leaders writing conflicting data simultaneously will silently corrupt the system. Apache ZooKeeper solves this coordination problem by abandoning blocking locks altogether. Instead, it provides a highly available, wait-free coordination service. To maintain exact consistency without locking, ZooKeeper relies on a highly specialized internal consensus engine, the ZooKeeper Atomic Broadcast Protocol, or ZAB. Preventing distributed chaos requires dropping mechanisms that halt the system. True coordination demands a strictly ordered configuration service that never stops processing. ZooKeeper does not expose raw consensus math to the user. Instead, clients interact with a hierarchical, Unix-like namespace of data nodes, known as ZNodes. These ZNodes are not designed for bulk data storage. They hold lightweight coordination metadata. Each node tracks its exact state through version numbers, data length, and timestamps. ZooKeeper assigns strict behavioral rules to these nodes. An ephemeral node has a lifespan tied directly to an active client session. If a client creates an ephemeral node to signal its active status, and that client's network connection drops, the server automatically deletes the node. Clients can also create sequential nodes. If multiple machines race to claim a resource at the exact same millisecond, ZooKeeper appends a monotonically increasing counter to each node name, instantly ordering the concurrent requests and preventing naming collisions. If thousands of clients need to know when a node changes state, they could continuously poll the server. But this creates a herd effect, saturating the network with redundant requests and crippling performance. To eliminate the herd effect, ZooKeeper uses watches. A client places a watch on a znode, and the server pushes a single edge-triggered notification only when a specific state change actually happens. By utilizing these wait-free structures, ephemeral lifetimes, sequence numbers, and watches, the mathematical burden of coordination shifts completely away from client-side application logic and into ZooKeeper's internal state engine. That internal engine operates across a cluster of servers known as a ZooKeeper ensemble. The ensemble relies on a strict quorum rule, meaning it requires a majority to function. In a typical 5-node cluster, 3 nodes form a quorum. Within this structure, one server acts as the leader, while the remaining servers act as followers. Any follower can serve read requests using its local memory replica, allowing the system to scale its read capacity efficiently. However, all write requests, any mutation to the state, must be strictly funneled to the leader. To replicate those write requests across the ensemble safely, the leader utilizes the ZAB protocol. ZAB enforces primary order atomic broadcast. Because state changes, like incrementing a node's version number, are incremental and mathematically dependent on the previous state, they cannot be processed out of sequence. They must be delivered in the exact order generated by the leader. Funneling all updates through a single leader via ZAB is the only way to guarantee a deterministic, unforgeable history of the cluster's state. ZooKeeper tracks that strict order using the ZooKeeper Transaction ID, or ZXID. The ZXID is a 64-bit integer divided into 2 distinct halves. The high-order bits track the leader epoch, representing the current leadership term. The low-order bits function as a transaction counter for every proposed change. If the active leader crashes, phase 0 of the ZAB protocol, fast leader election, is immediately triggered. The surviving nodes transition into a looking state and begin exchanging votes to find a replacement. The first rule of this election hierarchy relies on the epoch. The nodes compare their histories, and the node presenting the highest leader epoch wins the vote. If the epochs are equal, the logic shifts to the transaction counter. The node with the highest counter has the most complete, up-to-date history of the cluster, making it the rightful leader. If both halves of the ZXID are identical, the protocol uses the pre-assigned server ID as the final tiebreaker, granting leadership to the node with the highest ID. This epoch structure mathematically immunizes the system against split brain. If a network partition resolves and an isolated zombie leader attempts to broadcast old data, the quorum will immediately reject it because its epoch is outdated. The ZZZ operates as a monotonic, unforgeable clock that dictates the absolute truth of the cluster, maintaining integrity through any combination of hardware failures. Electing a leader does not immediately open the cluster to client traffic. First, the ensemble must enter Phase 1, Discovery. During Discovery, followers send their last accepted epoch to the prospective leader. This allows the new leader to establish the correct, unified history of transactions across the quorum. Next is Phase 2, Synchronization. The leader increments the epoch to mark its new term, resets the transaction counter to 0, and begins aligning the cluster by pushing out sync messages. The followers verify this new epoch, absorb any missing transactions into their local databases, and return an acknowledgement to the leader. The ZAB protocol executes the ready function only when a majority quorum of followers is perfectly synchronized with the leader. With the cluster aligned, it enters Phase 3, Broadcast, handling normal high-throughput client write requests. When a write request arrives, the leader generates a new proposal, increments the ZXID counter, and broadcasts it to the followers. To guarantee durability, followers must write this proposal to a persistent write-ahead log on their physical disk before they return an acknowledgement. Once a majority of ACKs are received, the leader issues a global commit message, finalizing the state change across the cluster. By combining this strict quorum pipeline with TCP's in-order network delivery, ZAB processes thousands of asynchronous operations simultaneously without ever violating its strict first-in, first-out integrity. This theoretical architecture powers some of the most data-intensive production environments in the world, including Apache Kafka. When a Kafka cluster boots up, it selects its active controller simply by having a broker race to create an ephemeral/controller ZNode. The first broker to create it wins the role. Because ZooKeeper exists, platforms like Kafka do not have to engineer their own complex Paxos or consensus algorithms from scratch. The severe computational challenges of mitigating network partitions, enforcing monotonic timing, and executing atomic broadcasts are entirely handled by the ZAB layer. True distributed coordination is achieved not by locking systems down, but by exposing simple, weight-free primitives backed by mathematically rigorous, strictly ordered replication.